Hello and welcome back. In today's video, I'm overclocking the AMD Ryzen Threadripper 7980X 64-core processor all the way up to 5750 MHz using the ASUS Pro WS TRX50-SAGE motherboard and EK Quantum custom loop water cooling. This will be the third time that I'm overclocking an AMD 64-core processor. I first overclocked the Threadripper 7980X in SkatterBencher number 36, and then I overclocked the Threadripper 5990X in SkatterBencher number 43. Those two processors were quite difficult to optimize, and I struggled quite a bit with them. But seems like Zen 4 Threadripper is much more accessible for optimization. Alright, let's get started. I hope you enjoyed the video. The Ryzen Threadripper 7980X is the flagship processor of AMD's Zen 4 based Ryzen Threadripper 7000 high-end desktop series codenamed Stormpeak. The Stormpeak processors were announced on October 19, 2023 and entered the market as two distinct segments. The Ryzen Threadrippers and the TRX50 chipset are designed for high-end desktop. In contrast, the Ryzen Threadripper Pro and the WRX90 chipset are designed for workstations. There are a couple of differences between the Threadripper and Threadripper Pro processors. Threadripper only supports up to 8 CCDs, so 64 cores, whereas Threadripper Pro supports up to 12 CCDs, or up to 96 cores. Threadripper only supports 4-channel memory, whereas Threadripper Pro has 8 memory channels. Threadripper supports up to 48 PCIe Gen 5 lanes, whereas Threadripper Pro has 112 PCIe Gen 5 lanes. The TRX50 and WRX90 chipsets are both promontory 21, so identical to the B650 chipset. The CCDs on the Ryzen Threadripper 7000 are the same as those on the Ryzen 7000 processors. There's just more of them. That means Zen 4 core architecture, 5nm TSMC process, DDR5 and PCIe Gen 5 support. The CPUs come with a new TR5 or SP6 socket. While there's a significant difference in pin count versus the Threadripper 5000 predecessor, thus making them physically incompatible, the physical size of the socket is the same. That means you can repurpose your old TR4 or SP3 thermal solutions as long as they can handle the 350 watt TDP, of course. The Ryzen Threadripper 7980X has 64 cores with 128 threads. The base frequency is 3.2 GHz and the listed maximum boost frequency is 5.1 GHz. However, the programmed IF-max is 5.65 GHz for one CCD and 5.35 GHz for the others. The C-state boost limiter restricts the core frequency to 4.8 GHz when 8 or more cores are active. The TDP is 350 watt and the TJ max is 95 degrees Celsius. In this video, I'm covering 4 different overclocking strategies. First, we enable Precision Boost Overdrive 2 and enable DOCP. Second, we tune the frequency using the Precision Boost Overdrive 2 toolkit. Third, we try out the ASUS AI overclocking technology. And lastly, we try a manual overclock. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The Elma Labs EFC X9 is the bigger brother of the Elma Labs EFC and EFC SkatterBencher edition that I've used in many guides before. I monitor the ambient temperature, water temperature, and fan duty cycle, and I include those measurements in my Prime 95 stability test results. I also use the device to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC X9, and then I map the fan curve from 25 to 40 degrees water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether or not the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we have to check the performance at stock settings. The default Precision Boost 2 parameters for the Ryzen Threadripper 7980X are as follows. Here are the benchmark results at stock. When running Prime 95, small FFTs with AVX2 enabled, the average CPU core effective clock is 3065 MHz with 0.707 volts. The average CPU temperature is 50.2 degrees Celsius. The ambient and water temperature is 26.2 and 34.4 degrees Celsius. The average CPU package power is 349.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU core effective clock is 3367 MHz with 0.746 volts. The average CPU temperature is 50.1 degrees Celsius. The ambient and water temperature is 25.7 and 33.6 degrees Celsius. The average CPU package power is 349.5 watts. Going forward, I will not read out the Prime 95 results explicitly, but rather I'll compare with all of the different overclocking strategies and highlight the differences. Now, just like with the 3990X and the 5990X, both 64-core processors, sometimes Windows doesn't really scale that well with so many operating threads. So from a performance tuning perspective, it makes sense to see if there's any performance difference when we disable SMT. To run stock with SMT disabled, you first have to go into the BIOS and go to the AMD CBS menu, enter the CPU Common Options submenu, enter the Thread Enablement submenu, set SMT control to disabled, then save and exit the BIOS. We reran the benchmarks and checked the performance compared to the default operation. Similar to the Ryzen Threadripper 7980X and Ryzen Threadripper 5980X we tested before, some benchmark applications perform better when we disable SMT. Most notably, we see a plus 23% performance uplift in V-Ray 5. However, in some benchmarks, we see a performance downgrade. For example, our CPU-Z multi-thread performance is down 21%. When comparing the Prime 95 results, we find that disabling SMT provides additional performance headroom in both AVX and non-AVX workload scenarios. The Precision Boost algorithm boosts the frequency 276 MHz higher in an all-core multi-threaded workload. That's possible because disabling SMT creates additional voltage headroom within the Precision Boost limits. This extra voltage headroom then translates into higher clock frequencies. It's important to note that unlike with the Threadripper 5990X, where the TDC and the EDC were the primary performance limiters, the Threadripper 7980X is primarily limited by the PPT or by the power consumption. Obviously, we can change that power consumption limit by using Precision Boost Overdrive 2, and that's exactly what we'll do in our first overclocking strategy. But before we start overclocking, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply leverage enabling Precision Boost Overdrive 2 and enabling ASUS DOCP. With the launch of Zen 3, AMD launched an improved version of its Overclockers Toolkit, Precision Boost Overdrive, that allows customers to fine-tune the Precision Boost frequency boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost, Override, and Scaler, Precision Boost Overdrive 2 also introduced Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. AMD's stock values, which can be set by disabling PBO, the motherboard vendor values, which are programmed into the BIOS to match the motherboard VRM specification and can be set by enabling PBO, and custom values, which can be programmed by the end user. I most recently took a deep dive in tuning Precision Boost Overdrive in my AMD Raphael or AMD Ryzen 7000 launch content. If you want to learn how Precision Boost and Precision Boost Overdrive works, I suggest you check out that video. In this strategy, we're simply enabling Precision Boost Overdrive, and thus we rely on the motherboard's pre-programmed values. We find that the following PBO values have changed. Increasing the PPT and, to a lesser extent, the TDC and EDC limit will help unleash the frequency and multi-threaded workloads previously limited by the PPT. DOCP stands for Direct Overclock Profile, and it's an ASUS technology that aims to replicate the AMD Expo behavior. AMD Expo allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports Expo, you can enable higher performance with essentially the click of a single button, so it saves you from a lot of manual configuration. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP1. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation with both SMT enabled and disabled. We get significant performance gains in all multi-threaded benchmark applications by enabling Precision Boost Overdrive. The highest performance increase is in V-Ray 5 with plus 36.41% over stock performance. In light multi-threaded applications, however, we only see minor performance improvement. In Prime 95, by enabling Precision Boost Overdrive, we get a ridiculous performance improvement across the board. Across all Prime 95 configurations, we get an additional 1 GHz of performance. With SMT and AVX enabled, we almost get 1.3 GHz higher frequency. That's incredible. Another thing to note is that the limiting factor is our CPU temperature. Despite running two 360mm radiators and 6 fans at 100% fan speed, the water temperature exceeds 40 degrees Celsius. That means there's no more thermal dissipation capacity left in this cooling rig. In our second overclocking strategy, we manually fine-tune the AMD Precision Boost frequency boosting algorithm using the Precision Boost Overdrive 2 Overclockers toolkit. Fused Maximum Frequency, or Fmax, is one of the Precision Boost infrastructure performance limiters. Essentially, the Fmax tells the CPU what is the maximum allowed frequency for each of the different cores inside your CPU. Boost Clock Override, or Fmax Override, is one of the overclocking tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. We need to make two important points about the Boost Clock Override. First, the override only adjusts the upper ceiling of the frequency and doesn't act as a frequency offset. Ultimately, the Precision Boost 2 algorithm still determines the actual operating frequency. 2. Each CCD can have its own programmed Fmax limit. We already saw this with the multi-die Ryzen 7000X3 processors. The same applies to the Ryzen Threadripper 7000X processors. Even though the listed maximum boost frequency for the AMD Ryzen Threadripper 7980X is 5.1 GHz, the programmed boost limit is 5.65 GHz for CCD0 and 5.35 GHz for CCDs 1 to 7. When we increase the Fmax boost limit by 200 MHz, CCD0's new Fmax is 5.85 GHz, and the other CCDs have a new boost limit of 5.55 GHz. Just like the mainstream desktop Ryzen 7000, AMD Ryzen Threadripper 7000 multi-core performance is constrained by the C-state boost limiter. I spoke at length about the C-state boost limiter in a standalone video on this channel. Long story short, the C-state boost limiter is yet another Precision Boost infrastructure limiter, and it governs what is the maximum frequency when a number of cores are active. For the Ryzen Threadripper 7000, the C-state boost limiter caps the maximum frequency when more than 8 cores are active, and on this 7980X, it caps that frequency to 4.8 GHz. For Ryzen 7000, the C-state boost limiter was enabled on the launch AGISA code. However, the ASUS ROG team developed a medium load boosted feature to work around this problem. On later AGISA versions, it appears that AMD disabled the C-state boost limit. Unfortunately, on a Ryzen Threadripper 7000, we cannot work around the C-state boost limiter by using the ASUS medium load boosted trick. However, when we increase the if max boost override, the C-state boost limit is also offset. So you can boost to 5 GHz when 8 or more cores are active. Curve Optimizer is an important new feature of the Precision Boost Overdrive 2 Overclocker's toolkit. Essentially, Curve Optimizer allows end users to fine-tune every core's VFT curve or voltage frequency temperature curve. The VFT curve defines what voltage is required for a certain frequency at a certain temperature. The higher the frequency and the higher the temperature, the more voltage is required to run that frequency stably. Curve Optimizer adjusts the VFT curve by offsetting the voltages of the factory-fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. The traditional approach to AMD Ryzen overclocking nowadays is to tune with a negative curve optimizer. Two things happen when you apply a negative curve optimizer. First, you tell the CPU that it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. On the Ryzen Threadripper 7000, Curve Optimizer is available per CPU, per CCD, or per core. The new feature, per CCD Curve Optimizer tuning, offers extra flexibility. However, mixing and matching with per core tuning is not possible. So you tune the Curve Optimizer per CPU, per core, or per CCD, but not some chiplets per CCD and others per core. The manual tuning process for Curve Optimizer can become quite convoluted since it affects the CPU core voltage in all scenarios, ranging from very light single-threaded workloads to heavy all-core workloads. Usually I spend a lot of time on per-core curve optimization, but for this platform I didn't have that much time available, so I took a more straightforward approach. I started with a negative curve optimizer of -15, then tried Prime 95 small FFTs with AVX2 on each core for a few seconds. I increased the negative curve optimizer magnitude by 5 steps for the cores that didn't crash. I reduced the negative curve optimizer magnitude by 5 steps for the cores that did crash. Once I had all cores dialed in, I ran another Prime 95 small FFTs with AVX and SMT disabled. The goal was to pass for 30 minutes without any core failing or clock stretching. Again, when a core fails, I reduce the negative curve optimizer magnitude by 5 steps. This whole process lasted about an afternoon. Let me know if you want to see me do this in a live stream with the 96-core CPU. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP 1. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override Plus to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. Set Core 0 to Core 63 Curve Optimizer sign to negative. I set the Curve Optimizer magnitude for each core according to my own test result. The Curve Optimizer ranges from -5 to -30. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation with both SMT enabled and disabled. We get significant performance gains in all multi-threaded benchmark applications by simply tuning Precision Boost Overdrive with Curve Optimizer. The highest performance increase is in V-Ray 5 with a plus 43.46% improvement compared to stock when we disable SMT. We also get a slight improvement in tests that only uses a few cores, for example plus 6.46% in CPU-Z. In Prime 95 we get another significant boost from tuning Precision Boost Overdrive. The Fmax override and curve optimizer combination gives us another 275 MHz when AVX2 is enabled and SMT disabled. But the most impressive result for me is the average of 4.9 GHz across all cores in Prime 95 non-AVX and SMT disabled. Yes, that's right.
all 64 cores running Prime 95 at 4.9 GHz. Admittedly, we also get a hefty increase in power consumption. 64 cores at 4.9 GHz is pulling about 900 watts.
Before we move on to our next overclocking strategy, I would like to discuss the Prime 95 stability test results. I already mentioned it a couple of times during this video, but this is the third time that I'm overclocking a 64-core Ryzen Threadripper. I overclocked the Zen 2 3990X, the Zen 3 5990X, and now the Zen 4 7980X. And I think it's worth bringing together all of these Prime 95 data points and see how AMD has evolved in providing us with more compute power.
The comparison rules are straightforward. I take the results from each overclocking guide with the most tuned PBO strategy. For each of these three platforms, it means unlocking the power limits and letting the CPU run until it's limited by the TJ max, which is 95 degrees Celsius for each CPU. Then we compare the average CPU core effective clock frequency during a 30-minute Prime 95 workload. We compare two scenarios: Prime 95 small FFTs with AVX2 and SMT enabled, and Prime 95 small FFTs with AVX and SMT disabled.
Note that this is not a one-to-one absolutely fair comparison. The cooling mechanisms have changed throughout my overclocking guides, and I didn't retest any of the systems specifically for this comparison. So take it for what it is.
If we look at the frequency in the heaviest workload, Prime 95 small FFTs with AVX2 and SMT enabled, then the frequency improvement is remarkable. With the Zen 2 64 core, we could run almost 3.3 GHz. With the Zen 3 slightly over 3.8 GHz, and with the Zen 4 chip, we can almost run 4.6 GHz. That's 1.3 GHz more than Zen 2 and 800 MHz more than Zen 3. If we look at the frequency in a more moderate workload, Prime 95 small FFTs with AVX and SMT disabled, then the frequency improvement is still impressive. With the Zen 2 64 core, we could run at almost 3.9 GHz. With Zen 3, slightly over 4 GHz. But with the Zen 4 chip, we can run a little over 4.9 GHz. That's about a 1 GHz improvement.
This frequency improvement is a combination of many factors.
The first significant contributor is improvements in the manufacturing process, which shift the voltage frequency curve in favor of higher frequencies at a given voltage. We can see this very well with the Ryzen Threadripper. In the heavy Prime 95 workloads, the optimum voltage stays the same even though the Zen 4 7980X, built on TSMC 5N, runs at significantly higher frequencies. A second major contributor is the ability to deliver substantial power to the CPU cores. I know it's popular nowadays to comment negatively on CPUs with high power consumption. Still, from a business perspective, using slightly more power on one CPU to meet a particular performance target is better than having to use multiple CPUs and multiple motherboards. So, CPU and platform engineers must figure out how to reliably deliver such high power to the CPU. As we can see from the data, the Zen 4 Ryzen Threadripper can push substantially more power through the 8 CPU chiplets. That's mostly down to the VRM, I suspect. With Zen 2 and Zen 3 Ryzen Threadripper, the TDC, EDC, and VRM temperature were key limiting factors when overclocking. For Zen 4, AMD has moved to 2 VDDCR CPU voltage rails to power the CPU cores, thereby significantly reducing the load on the CPU core voltage plane.
Anyway, that's enough about Prime 95. Let's move on to our next overclocking strategy. We use the ASUS AI overclocking feature integrated in the ASUS BIOS in our third overclocking strategy. For many years, motherboard vendors have tried to implement automatic overclocking technologies into their BIOS to provide a more straightforward way of enhancing the system's performance. But more often than not, these OC profiles would either target a frequency that's way too aggressive or use too much voltage to kind of guarantee stability. So you'd end up with either an unstable system due to too high frequency or an overheating system due to too much voltage.
ASUS AI overclocking uses a unique strategy for automatic overclocking. Instead of working with preset frequency and voltage profiles, the system will monitor the CPU and cooling system throughout an initial testing phase. Based on its findings, it will then predict the optimal settings. The system automatically guides the overclocking process and adjusts voltages and frequency to match your cooling system. The better your cooling, the higher your AI overclock. There are 3 steps to enabling AI overclocking. First, reset the BIOS to default settings. Then, reboot and enter the operating system. Run a couple of heavy workloads, such as Prime 95 or Cinebench, for 10 to 30 minutes. Then return to the BIOS and enable AI overclock when ready. In addition to automatic overclocking, AI overclocking provides advanced information and suggestions in the AI features menu. The information includes the following. The SP value is based on the maximum boost frequency, temperature, and P0 VID combination. A higher SP value would indicate a better quality core with superior overclocking capabilities, though it's not an exact science. The overclocking suggestions are based on a continued evaluation of your CPU thermal solution. After enabling AI overclock, the following settings have changed. As you can see, AI overclock provides a conservative plus 100 MHz increase of the precision boost maximum frequency. It also boosts the CPU to 4872 MHz in all core workloads by enabling Dynamic OC Switcher. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP 1. Set CPU core ratio to AI Optimized. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Enabling AI overclocking gives us a decent performance bump, especially in multi-threaded benchmark applications. We get the highest boost in performance of plus 25.77% in Blender Classroom. Unfortunately, when running Prime 95 small FFTs, either with AVX2 enabled or AVX disabled, the CPU is not stable. AI overclock targets the typical use case and stability requirements, not a worst case scenario like Prime 95 with AVX.
In our 4th overclocking strategy, we are pursuing a manual overclock. Now, I was a little bit short on time with this platform to do a really comprehensive overview of the manual tuning opportunities, so I focused on a single worst case scenario. Stability in Prime 95, small FFTs with AVX2 and SMT enabled.
One could question the use case for manually overclocking the Ryzen Threadripper CPUs. Just like with all Ryzen processors, the major downside of manual overclocking is that you lose the benefits of Precision Boost 2 technology in low-threaded benchmark applications. So, whereas this 7980X can boost up to 5650 MHz with Precision Boost, it will be limited to your highest manual frequency when manually overclocking. However, I believe there's a good use case for manual overclocking on the Ryzen Threadripper CPU, and that's for maximizing workload-specific performance. As I demonstrated in SkatterBencher number 43 with the Zen 3 Ryzen Threadripper, optimizing a specific workload can yield another 10 to 20% more performance compared to relying on a tuned Precision Boost algorithm.
Let's have a closer look at the Stormpeak architecture to better understand the tuning opportunities embedded in this Ryzen Threadripper 7980X processor.
The Ryzen Threadripper 7980X is AMD's Stormpeak Zen 4 based flagship high-end desktop CPU. Stormpeak is derived from the EPYC Genoa server product line and may feature up to 13 chips on package, 12 CCDs and a single I/O die. CCD stands for Core Chiplet Die and is a die on the Ryzen CPU with CPU cores. The Zen cores are packed together in a CCX or core complex. A Zen 4 CCX consists of up to 8 individual cores, each with its L1 and L2 cache and a shared 32 MB of L3 cache. The frequency of the CPU cores is driven by a 100 MHz reference clock input. Each CCX has its own PLL and thus can run an independent frequency. The cores within a CCX share the same PLL, so they'll run at the same frequency. That means for the Ryzen Threadripper 7980X, we can set an independent frequency for each of the 8 CCXs. Ironically, that means we have less tuning granularity than with the Zen 2 Ryzen Threadripper 3990X, as Zen 2 has 2 CCXs in one CCD and thus double the CCX frequency tuning capabilities. The voltage of the CPU cores is provided by not one but 2 VDDCR CPU voltage rails. This is a significant change from previous Ryzen Threadripper platforms and will undoubtedly impact the overclocking experience. The main advantage of adding an extra voltage plane is that it's much less taxing on the VRM. In case you missed my SkatterBencher number 43 overclocking guide with the Ryzen Threadripper 7980X, a key limiting issue for reaching maximum performance on the previous gen was that under overclocked conditions, the EDC or electrical design current would peak over 800 amps. That would trigger the VRM OCP and shut down the system. The current draw is now split between two power planes. The current draw per power plane also halves. So as a result, there's no more VRM limitation when overclocking, not even when you push all 64 cores to their limit.
Choosing the right voltage for your manual overclock is always a trade-off between increasing the overclocking potential, managing the extra thermal challenges that come with increased voltages, and of course, considering the CPU lifespan. It's with that last thought that we kick off what's arguably the most tedious or the most exciting part of Ryzen Threadripper overclocking, per CCX frequency tuning.
Our limiting factor will ultimately be the cooling solution as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So the first step in our tuning process would be to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CPU ratio of each CCX. Simply increase the CPU ratio of one CCX until the application shows signs of instability, then back off. Do this for each CCX sequentially, and you'll end up with the maximum stable per CCX frequency for a given voltage. In this table, you can find the maximum ratio for each CCX of our CPU. As a reminder, the values in this table are for my specific system and a specific stability test. Your CPU may have wildly different values depending on the CPU sample, cooling and motherboard, and your chosen stability test. Now that we know the ins and outs of Ryzen Threadripper 7000 manual overclocking, let's jump into the BIOS. Upon entering the BIOS, go to the AI Tweaker menu. Set AI Overclock Tuner to DOCP 1. Enter the CPU core per CCX submenu. Set core VID 0 and 1 to 1.135. Set CCD0 CCX0 ratio to 48.50. Set CCD1 CCX0 ratio to 47.50. Set CCD2 CCX0 ratio to 46. Set CCD3 CCX0 ratio to 47.50. Set CCD4 CCX0 ratio to 47.75. Set CCD5 CCX0 ratio to 47. Set CCD6 CCX0 ratio to 47. Set CCD7 CCX0 ratio to 47.75. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. As we're used to with AMD Ryzen, manual overclocking has the significant drawback of losing the single-threaded performance we get with Precision Boost. Whereas even at stock, the CPU cores can boost up to 5.65 GHz, with our manual overclock, we only reach a maximum of 4,850 MHz. That translates into about 10% performance loss in single-threaded applications. However, in multi-threaded applications, our manual overclock provides a decent performance uplift of up to plus 26.39% in Blender Classroom. With manual tuning, we can squeeze out another 160 MHz in the most intense Prime 95 workload variant. We now have all 128 threads running Prime 95 AVX2 over 4.7 GHz. That's pretty impressive. What's more, in Prime 95 small FFTs without AVX, our system runs about 80 MHz less compared to using Precision Boost Overdrive. However, we do this at an incredible 14 degrees Celsius lower temperature and 240 watt lower power consumption.
Alright, let's wrap this up. Unfortunately, I didn't have that much time on my hands to explore everything that Ryzen Threadripper 7000 has to offer. But based on my limited hands-on experience, I would say that this platform is very impressive, both from the performance side of things as well as from the ease of tuning side of things. This is the third time that I'm overclocking a 64-core AMD Ryzen Threadripper processor. I remember very well with the Zen 2 3990X and with the Zen 3 5990X how challenging those platforms were. And I just don't have those challenges with the Threadripper 7000. I also remember being so happy that I was finally able to see 4 GHz on all 64 cores on the 5990X. And with the Ryzen Threadripper 7980X, we're close to 5 GHz on all cores. Yeah, that's right. We're only 100 megahertz away from 5 GHz on all 64 cores. That's incredible. I think the main contributor to how much easier it is to overclock the Ryzen Threadripper 7000 are these dual VDDCR CPU voltage rails. With extending the voltage planes from 1 to 2, AMD has essentially eliminated the main bottleneck that was constraining the performance of the 3990X and the 5990X, and that's the VRM. So now with the 7980X, even if you push all 64 cores to the max, the VRM isn't really the issue anymore. Anyway, that's it for today. I still plan to also have a look at overclocking the 96 core at some point in the future. So stay tuned for that if you're interested in seeing me take on that monster of a CPU. If you have any questions or comments, drop them in the comment section below. As per usual, I'll also put up a written version of this video on my blog. And I want to thank you for watching and of course the patrons for the support, and see you next time.